All right, we're gonna crank some group theory problems. Why didn't I just eliminate that? Oh God, what did I just eliminate? All right, whatever. I thought I just got rid of that. Okay, so we're gonna do number 1 first. Let G be a group A and B, B and G. Prove that there is an automorphism phi of. Okay. Yes, I've already done this problem before. I'm doing it again. All right. Group theory, number 1. We're going to do the first problem. Let G be a group. Let A and B be and G. Prove that there exists an automorphism phi from G to G such that phi of A, B is equal to BA. Okay. And I'll try to live compile as I do this. All right. So we're going to start. Okay, so we want to first let G be a group. And we want to define some map from G to G. So it's an automorphism by phi of G is equal to BG B inverse. Okay, and we can kind of test it in our head and see if that works. You know, if I put a B in there, we'd get, you know, a B on the right, and then I can compile this so you can see it as well. So you definitely get, I mean, a B on the right, and that B on a B on the left and the B on the right would cancel out by the negative B. So this is definitely the map we want. I guess for G and B and G, even though it's set in the problem, I'll just restate it in our solution, so we're all clean. Okay, yeah, for G and B and G. Okay, so we want to show it's an automorphism, hence we want to show it's an isomorphism, so we want homomorphism, injective, and surjective. We'll start with homomorphism. Pick 2 elements in the group. Then look at the product of p's. We get something that looks like this. But you'll notice those middle terms, the B inverse and B, cancel out, and so we just get what we want, which is definitely phi of x bar. So any 2 arbitrary elements in the group, their product maps to the, you know, the image of the product maps to the product of the images as desired. Yep. Okay. Hence, phi is a homomorphism. So one thing down. We'll do injective next. Suppose phi of x equals phi of y, and maybe I should, you know, define other variables, but it won't really matter. Then we have that bx B inverse equals by B inverse. Multiplying on the left by B inverse and on the right by B, we get x equals y. Thus, phi is injective. Okay, so we have an injective homomorphism. Let's see if this compiles. Okay, we have an injective homomorphism. It remains to show that it's surjective. Observe that phi of, let's do B inverse GB is equal to, it's going to put B on the right, and then B inverse GB, and then a B inverse on the, so I keep saying right and left backwards, but yeah, and then the inverses will cancel out, leaving us with just the G. Let's see. So we have that phi is surjective, therefore phi is an automorphism. Okay, and then we'll just explicitly state why this condition works. So I can scroll up so you can see the problem. Remark that phi of AB is equal to BAB B inverse. Maybe I should use parentheses there, but that's definitely BA when you simplify. Okay, so I don't like how that cuts off, so simple latex fix, put it in double math mode. Okay. Cool. So this is part A. I guess I'll label that part A. And we want to do a part B. Prove that AB and BA have the same order. Okay, I'm going to use what I learned in A, which was that let the order of AB equal n, then AB to the n is equal to E. So, okay. So we have that the identity is equal to phi of the identity, which is equal to phi of AB. Let's do it like this. Phi of AB to the n. Okay, but since we have phi is a homomorphism, we can bring that n on the outside. Phi AB to the n. Yep. I'll justify this since phi is a homomorphism. Thus, the order of phi of AB is less than or equal to, let's see, let me compile. Haven't compiled in a while. Okay, so we said that the order of AB was n, so we have this. Okay, so we get this. So the order of phi of AB is less than or equal to n, which is just the order of AB. So I'm just going to say the order of AB. But we also know that phi of AB, in A, we proved that that is the same thing as BA. So we have that BA is less than or equal to AB. Okay, let me compile that. And if we were to reversing the roles of AB for BA, so do the exact same proof, but do everything with BA equaling AB. We could use the exact same logic to say that reversing the roles for of AB for BA, we have that AB is equal to phi of BA. It's just the backwards of the other guy, which is less than or equal to BA. Therefore, they're equal. The order AB is equal to the order of BA. Yeah, because they're both less than or equal to each other, so they have to be equal. Okay, and that's the entirety of number 1.